In this class, we'll study the free vibrations of a 2 degree of freedom system. We have, in this example given, you have two masses M1 and M2. They are separate. They have three springs, and by taking the free body diagram of M1 and M2, we will develop the corresponding two equations of motion corresponding to mass M1. Let us say x1 and x2 are on the right side taken to be positive towards the right hand side, and we also at this stage assume forces F1 and F2, some harmonic forces, to be also present. These are the then we can develop the general equations of motion. Later on we'll make F1 and F2 both equal to 0, so that we have the situation of a free vibration of 2 degrees of freedom. Okay, corresponding to the first mass M1, the forces acting are F1, and the force due to K1, spring K1, is acting to the left, and also when x1 is greater than x2, the spring K2 gets compressed and there is a force M1 acting to the left. Therefore, you have the first equation of motion given by F1 minus K1 x1 minus K2 into x1 minus x2. This is the resultant force on the left hand side that will lead to an acceleration of the mass M1 x1 double dot. Okay. Similarly, we write the equation of motion for M2 given by F2 minus K3 x2, because x2 is to the right, K3 spring is compressed. Therefore, it will lead to a force to the left side and mass M2. Similarly, you also have K2 into x1 minus x2. Therefore, this resultant force will lead to an acceleration of the mass M2 by x2 double dot. So, these two are the two equations of motion. Well, the equations are now reframed as given by the equation set B, where F1 and F2 are brought to the right side of the equation. Now we will make F1 and F2 to be equal to both 0, so that we have a free vibration case. Well, in the case of free vibration, let us say the whole system, including the mass M1 and M2, is under a harmonic motion at a frequency omega. That is, and let us say the amplitude of x1 is a1 and amplitude of x2 is a2. Therefore, we have x1 is equal to a sin omega t and x2 equal to a2 sin omega t. Or we have the acceleration given by minus a1 omega square sin omega t and x2 double dot equal to minus a2 omega square sin omega t. Okay, now if you substitute x1 and x1 double dots in the two equations of motion of set B with F1 and F2 both equal to 0, we have the equations given by K1 plus K2 minus M1 omega square into A1 minus K2A2 equal to 0, and the second equation being minus K2A1 plus K2 plus K3 minus M2 omega square into A2 equal to 0. In both of these equations, we will find that we have removed sin omega t that appears in each of the terms. Now, well, from the previous equations, we also get the ratio of the amplitudes of masses m1 and m2, a1 by a2. They both are given by a1 by a2 is equal to k2 over k1 plus k2 minus m1 omega square, which is also equal to, from the second equation, k2 plus k3 minus m2 omega square by k2. Well, when we equate from this equation, when you manipulate, you will get that is, you cross multiply these two, you will get omega 4. After a bit of manipulation, you will get the equation in this form: omega 4 minus k1 plus k2 by m1 plus k2 plus k3 by m2 times omega square plus k1 k2 plus k2 k3 plus k3 k1 divided by m1 m2 equal to 0. This is called the frequency equation, which is in the fourth order of omega, fourth power of omega, and this leads to solution of this equation leads to omega 1 square and omega 2 square, which have both positive and negative values, and we neglect the negative values of omega 1 and omega 2, and that leads to two positive values of omega 1 and omega 2. which are the two natural frequencies of this 2 degree of freedom system. Well, when we substitute omega in any of this, either this or this expression, uh, corresponding to 1 omega 1, you will get 1 amplitude ratio. Corresponding to omega 2, you get the second amplitude ratio. Basically, in this 2 degrees of freedom system, our job will be to study the two, to find out the two natural frequencies, and also to find the amplitude ratios, including also what is known as the points if there are any nodes. For example, we will take an example where the three springs have are equal in spring constant, and the two masses are m each. Well, when you substitute these values in the fourth order frequency equation, you will find that because K1, K2, K3 are all equal to K, and M1, M2 both are equal to M, we will get this expression omega 4 minus 4K over M omega square plus 3K square by M square equal to 0. When you solve this, you get omega 1 square and omega 2 square. Taking the positive values, you will get omega 1 equal to root K by M, and the second natural frequency is root 3K by M. This K by M is the lower of the two values, and that's called the fundamental frequency of this 2 degree of freedom system. So basically, you have found out the two natural frequencies. They are simply given by the two values. They are in terms of the two values K and M. Well, as you have seen earlier, substituting omega 1 equal to K over M in the amplitude ratio expression, we will get K2 plus K3 over M2 omega 1 square by K2. In this, we substitute K2, K3, etc. as K, and M2 as M, and omega 1 as root K by M. That will lead us to plus 1. That means the two amplitudes, the amplitude of M1 and also this M2, uh, both of these masses are in the same direction. That means the whenever this goes to a positive side, M2 also goes to a positive side. Basically, in the vibrations like this, and here the amplitudes take place in the same direction, and the magnitude of the two amplitudes are equal, naturally, because this will be a very symmetric system you have taken. So in one case where omega 1 under the first natural frequency root K by M, you find that the amplitude ratio is plus 1. Well, the way you draw the diagram for the amplitudes is under M1, you take a value of 1 unity, and because it is plus 1, A1 by A2 is plus 1, you draw 1 here, and because at the ends there is no motion, naturally there is 0 here, also here 0, so you draw a line up to 1, again this is also 1. This is the amplitude diagram. Well, in the second case, when omega 2 is equal to root 3K by M, you use the same expression for A1 by A2 equal to this. In that, when you do that, when you substitute the values, you will find that A1 by A2 is minus 1, meaning A1 and A2 are in opposite directions. That is, when M1 oscillates to the right, M2 will be oscillating to the left. So that will lead us, but the magnitudes are the same, they are just in opposite direction. Therefore, when A1 is plus 1, A2 will be, rather M2 will be minus 1. So the amplitude diagram will be like this. This is actually called the modal diagram. This is called the mode shape, and this is called the mode shape in the second natural frequency. In the second natural frequency, you will find that there is a point called the node, which experiences zero oscillation. So there is a point here in the center of this spring which doesn't go through any oscillation at all, and that is represented graphically in this diagram as the node. This is called the node. Okay, so we have studied a case where the three spring constants are the same and the two masses are the same. Well, you could also take another case. Suppose this could, if K3 were 0,